Chapter 8, High Power Switching, starting by looking at the thyristor. Now, before we look at the thyristor, it's a type of switch, we do need to kind of review a transistor switch. We need to recap this. I would recommend that you pause the video and have a go at this question in your own time. It shouldn't take you more than 10 minutes. Okay, hopefully you've had a go at this yourself now. So let's have a go at this question. I'm going to go slide. That's writing on it. So we know that there's 0.7 volts between the base and the emitter. And we know that there is in total 4.2 volts. So that means that there must be 3.5 volts left because we've got 4.2 minus 0.7. So that's 3.5 volts. So for part A, the voltage across the resistor is 3.5 volts. For part B, we're asked to work out the base current. This is rated at 800 milliamps. So the collector current is 800 milliamps. And we're also told that the gain in the question is 200, quite a nice large gain. Remember that transistors are effectively current amplifiers. They boost the current. So we have this equation. So this is on your data sheet, of course. So we've got 800 milliamps is equal to 200 times IB. So the base current is 4 milliamps. So part C, what's the ideal resistance? R is V over I. So we've got 3.5 volts going across the resistor and 4 milliamps. So we get 875 ohms. Part D, it asks for the E24 value. And we've got two choices here. We've got either 820 or 910. 910 is closer. If we were looking at a timing circuit, I'd say take the closest value to get the time as close as possible. But in this case, we're trying to make sure that we've got our switch fully on at 4.2 volts as the input voltage. So remember that V equals IR. The input voltage is set. So if we have a lower resistor, we're going to have a higher current, which is what we want. So this current is the minimum current to saturate it at the 4 milliamps. We don't want less than that. So if we go with a higher resistor, we end up with a lower current, which is not what we want at all. So we are going to choose the 820 ohm resistor. Part E asks us to sketch the input voltage against the output voltage. Now remember that this is a switching unit, but we measure the output voltage over the transistor, which is a little bit counterintuitive. So this is the load voltage is the one we're trying to maximize, not the output voltage. So when the switch is off, the output voltage is the supply voltage of 6 volts and nothing's going over the load. When it's on, the output voltage is 0 and all the voltage is going across the load. So it starts off until it gets to 0.7 volts. Remember, that's the voltage at which it starts to conduct. And then got this lovely linear region until the 4.2 volts. That's the point when it's saturated, as we were told in the question. So this is on, this is off, and this bit in the middle is the linear region, which is the problem region. The linear region is a problem because we end up with a significant amount of power being dissipated in the transistor. So when it's on, it has no voltage, P equals IV, but if V is 0, then P is 0. So that's on. And off, sorry, this is slightly messy. Off is also fine because the current's 0. There's no current flowing. So I is 0, P is again 0. So everything's good, no power dissipation, no inefficiencies, no heat problems. The problem is the linear region, because there will be both current and voltage. And part F gets us to think about that. This is the same diagram, but done on graph paper, so it's a bit accurate. And we're asked to work out what happens at 3 volts. I draw across at 3 volts, and we've got it's about 2.2 volts, slightly below 2.25. That's 2.5 in the middle. So that is the voltage across the transistor, which means that 6 minus 2.2 is 3.8. So we've got 3.8 volts left for the solenoid. If you're unsure about these calculations, please do pause it, rewind it, slow the speed down, or speed it up if you're comfortable. And we were told in the question that the solenoid has a resistance 7.5 ohms. So to work out the current flowing across the collector, across the solenoid, we can just do V over R. So that's 3.8 over 7.5, I think it was. Yeah, 7.5. So that's quite a large current of 0.506 recurring amps, or 506 milliamps. We can then use P equals IV because the collector current is pretty much the same current that's flowing to the emitter, because remember the base current is 200 times smaller, so basically ignore it. It's not nothing, but we can ignore it fairly safely. It's not going to have a massive impact. And the voltage is 2.2. So the power output is 1.11 watts, which is huge. You can see this is a big problem. This will obviously be a bigger problem if we're trying to do higher power systems. This is relatively low power solenoid at 6 volts, but you can have much higher ones, and then in the linear region we get a bigger problem, and the transistor will potentially melt. So for higher systems. So enter the thyristor. Thyristor is a type of diode. Hence, the symbol looks a lot like a diode. Our book likes to draw the line in the middle. You can do, you can not do, it doesn't really matter. It is a diode, type of diode. So this is an anode and this is a cathode. And it wants the voltage to go this way. So it's forward biased. And it really doesn't want the voltage to go the other way. The extra detail is the gate. And the gate lets us turn on the diode. Now the thyristor is turned on when we have a sufficient current and voltage going into the gate, as long as we get a large enough spike. And it can be a spike because it latches on, so as soon as it's on, it stays on. So as soon as we get a large enough spike in current and voltage, it goes on and it starts to conduct between the anode and the cathode. It stays on so long as we've got enough current and voltage flowing between the two. This is often called VAK, just to confuse us slightly. As long as those are large enough, it will keep flowing. So it's a self-latching system. Doesn't matter what you do to the gate at this point. You can put a large current and voltage back on it. It won't turn it off. You can even put negative values on. It won't have any impact. It self-latches once you've spiked it. As long as there's enough current and voltage flowing between anode and cathode, it's on. This is the kind of question that they ask about this. So working at the ideal resistor value, again, this is quite like that BT question we just had. So we've got 10 volts going through the system. This minimum of this is 0.8 volts, which means we've got 9.2 volts left to play with to go across the resistor. And we know that the minimum current is 0.2 milliamps. So we can do R is V over I. So that's 9.2 over 0.2 milliamps, which is 46 kiloohms. This is the maximum value. So if you're looking in the E24 series, you should choose a lower value. Because if you choose a higher value, it comes back to this V equals IR idea again. If you choose a bigger value, you end up with a lower current because the voltage is fixed. So you end up with lower than the minimum gate current to turn it on. So that's the kind of question you might get. What kind of resistors do we need to put into our circuit so that it works? You don't want too big a value because you can damage the thyristor. This is the characteristic curve of a thyristor. So the start of the curve before we apply the gate signal is basically off. There's pretty much no current flowing. If we put a massive voltage on it, we still get pretty much nothing. We get a tiny amount of current, but you are talking tiny. However, as soon as you have activated it, any amount of voltage and will create a really, really large current response. So it's acting like a low resistor. And this is acting like a high resistor, if you like. But that's not really too important. You need to remember that this is off. This is on. Simple as that. Do notice that there is a residual voltage drop between the anode and the cathode. So whilst you have turned it on and your load is usually drawn above, like with the BJT, you've still got 1 volt going across the device. There are advantages of this. So one advantage over the transistor is its self-latching. In a BJT, you need to keep that constant current on the base to keep it conducting, whereas this is on. Once you send that spike of current, it's on. So it's self-latching. Another advantage is that it can deal with high power. So it'll keep working and it won't have difficulties with that. And the switch on time, as you can see, is really quick. So you press the button, pretty much straight away you're on. You're good to go. So the linear region is tiny. It doesn't really have one. And you may be thinking, what about relays? Relays do, once you press the button, are on. And the advantage of this over a relay is that it doesn't have any moving parts. So a relay is a physical system, which means that the moving parts involved will wear out over time, whereas this is a solid state system. It's got the quantum mechanics, quantum physics behind it, which we look at in chapter 13 a little bit. So it doesn't really wear out. You can't really wear out the electrons and the holes flowing through it.